All right, let's jump right into a scientific detective story. And our setting is the coldest, most remote place on Earth. Something really strange is happening in the waters around Antarctica. It's a change that starts in just one corner, but it sends this ripple effect all the way around the continent and maybe, just maybe, across the entire globe.
So here's the central mystery. A huge part of the ocean is freshening up. It's literally becoming less salty. Now you might be thinking, okay, a remote patch of ocean is a little less salty, why should I care? Well, as we're about to find out, this could be a signal of a massive change for the whole planet. What happens in Antarctica? It definitely doesn't stay in Antarctica.
So our investigation starts at what you could almost call the scene of the crime. We're talking about a giant bay of icy water right at the bottom of the world, and it's here that scientists first realized, wait a minute, something's not right.
This is the Ross Sea. For years, oceanographers who are tracking the data here noticed this really consistent trend. Decade by decade, the water was slowly but surely losing its saltiness. Now you have to understand, salinity is like one of the ocean's vital signs. It helps drive currents, it shapes entire ecosystems. And the weird part was, the local weather, the ice conditions, none of it could fully explain this change. They had a genuine puzzle on their hands.
And here's the twist, the answer to the Ross Sea mystery. It wasn't in the Ross Sea at all. The trail of evidence started leading investigators to a completely different part of the continent, thousands of kilometers to the west. And this is where we find our prime suspect. Turns out, the source of all this fresh water wasn't some mysterious phenomenon. It was the West Antarctic ice sheet, which we now know is melting at a truly astonishing rate. The hotspots for this melting are in the Amundsen and Bellingshausen seas, and the way it's happening is just wild. This isn't about warmer air melting the ice from above, like you'd probably imagine. No, the real damage is happening completely out of sight, deep underwater. There's a current of relatively warm ocean water that is just eating away at the base of these massive ice shelves from the bottom up. And if you want to put a number on it, just try to wrap your head around this. The scientific model we're about to look at used a melt rate of 559 billion tons of fresh water pouring into the ocean every single year. And that's just from this one region. It is an almost unimaginable amount of water. So the scientists had their victim, the freshening Ross Sea, and they had their suspect, those melting glaciers way over to the west. But how on earth could they prove the connection? We're talking thousands of kilometers across some of the most treacherous ocean on the planet. Well, you can't exactly follow a single drop of water for decades in the real world, so they did the next best thing. They built a virtual one, an incredibly complex and realistic computer simulation of the entire Southern Ocean. And to really isolate the cause, they ran two different experiments. First, a baseline scenario they called LMLT, which had low ice melt, kind of like conditions back in the mid-20th century. Then they ran the CTRL, or control scenario, which represents our reality today, with that massive 559 billion ton a year melt rate. By comparing the two, they could see exactly what all that extra meltwater was doing. And here is the really clever part. Inside their virtual ocean, they released a passive tracer. You could just think of it like a brightly colored digital dye. They dropped it in at the exact spot where the glaciers were melting, and that let them track the plume of fresh water as it took its journey through the ocean currents.
So, what did they find? What did this digital dye reveal? Well, the simulation gives us the answer, showing the exact path and the impact of that meltwater over more than 3 decades.
And this shows the results perfectly. On the left, you've got the low melt world. On the right, our modern high melt world. After 32 simulated years, just look at the difference. That huge plume of colors spreading westward from the Amundsen Sea, that's our virtual dye. It shows exactly where all that fresh glacial meltwater traveled. The model didn't just show them where it went, but how long it took. It's amazing. The first signal hit the Ross Sea in just 1 year, solving our initial mystery. But the journey didn't stop there. It took 5 to 10 years to reach the other side of the continent, and up to 15 years to make it all the way around to the Weddell Sea. So let's actually watch this journey unfold. Just 5 years into the simulation, you can already see a difference. Those blue areas, they show a clear coastal current of less salty water that's already started its journey west, heading right for the Ross Sea. Okay, jump ahead another 5 years to the 10-year mark. The effect is undeniable now. That signal has gotten much stronger, and it's now flooding deep into the Ross Sea basin. This right here is the smoking gun. It proves the connection and solves that mystery that puzzled scientists for decades. But the journey isn't over. Fast forward to year 20, and that plume has traveled thousands of kilometers farther, still hugging the coastline of East Antarctica. It's really like a slow-motion freshwater river that's circling an entire continent.
And finally, after 32 years, the simulation shows the full incredible impact. The freshening signal stretches almost all the way around Antarctica, from its source in the west clear over to the vast Weddell Sea in the east. The connection is proven, the case is closed.
So, we've solved the Antarctic mystery. But so what? Why does a slightly less salty ocean around a remote continent matter to the rest of us? Well, this is where the story goes global. To understand why, you need to know about this stuff. Antarctic bottom water, or AABW. Think of it like the heart of the ocean. In a few key spots around Antarctica, the surface water gets incredibly cold and really salty, which makes it super dense. This heavy water then sinks, plunging all the way to the ocean floor. And that sinking motion is what kicks off a deep ocean current that circles the entire globe. So you can see the problem, right? What happens when you pour billions of tons of fresh, buoyant meltwater on top of that system? Well, it sets off a pretty simple chain reaction. That fresh water makes the surface layer less salty, which makes it less dense. And this lighter water, it struggles to sink. It just can't. And that effectively puts the brakes on the entire engine of deep water formation. And this is not just a local problem. The sinking of ABW is a critical engine for the entire global ocean conveyor belt. We're talking about a system of currents, including the famous AMOC in the Atlantic, that moves heat around the planet, transports nutrients that support marine life, and fundamentally regulates our global weather patterns. It is a very, very big deal. The scientists who ran the simulation put it in careful scientific terms, of course, but the implication here is huge. This massive freshwater journey around Antarctica isn't just changing the local water. It has the very real potential to weaken one of the planet's most important circulatory systems. And this journey leaves us with a final, pretty crucial thought. We've just uncovered one hidden connection. A freshwater trail linking a single melting region to the engine of our global oceans. It really forces you to ask, in our rapidly changing world, what other vital connections are being altered right now, before we even have a chance to discover they exist?